Let's find the highest common factor, or the greatest common factor, they mean the same thing, of 15 and 16. And we're going to use our method of prime factorization, so we're going to make prime factorization trees. So we do it like this. What times what is going to be 15? So if we know our times tables, we know 3 times 5. If we multiply those two numbers together, we get 15. You could try 15 and 1, but you won't get very far because that goes on forever and ever and ever. So you don't go with the same number as you're starting with and the number 1. Those aren't two very profitable factors to be getting on with. So we then look, after we've done that stage, we say, okay, the two factors we've identified, are any of them primes? In this case, 3 is a prime, so we would circle it. And 5 is also a prime, so we circle that. So prime numbers are numbers that can only be divided by itself and 1. So once we reach a prime number, we're finished. Okay, you can't go any further. The only way this could keep going is if you went 1 times 3, and it'll be 1 times 3 again, and it'll be 1 times 3 again, and it would never end. So once you reach a prime number, you're finished that particular branch of the prime factorization tree. So 15 is now done. What about 16 though? So if we go with 16, what times what equals 16? Well, let's go with 2 and 8. 2 is a prime number. Let's go with 2 times 4 equals 8. 2 is a prime number, and 2 times 2 will equal 4, and 2's are prime numbers. So we now say, right, which of these prime factors, 3 and 5, are also prime factors of 16? So are there any 3's with the 16 tree? And the answer is no. Are there any 5's with the 16 tree? The answer is no. So let's look at these primes. Are there any 2's that are in the 16 tree? Are there any 2's in the 15 tree? The answer is no. So they have no common prime factors. Now, where you have a situation where the two numbers that you're looking at do not share any prime factors, we know that the highest common factor has to be 1. That's as good as it gets.